Okay, let's get started. So I told you to explain to the redundancy today. So last time we start talking about Hamiltonian with delta function. Okay, this kind of Hamiltonian. And we try to solve this system. So it's called one-dimensional delta function with any particle and bosons with delta function and a boson delta function potential. And in one-dimensional. And then, so last time we look at the first of all, to just before solving any particle, we look at the two bosons. So then, so equation motion becomes like we made an ansatz that the wave function, so we want to solve the Schrödinger equation, where the wave function can be written as whatever a12 e to the I k1 x1 plus k2 x2 and plus a21 e to the I k2 x1 plus k1 x2. In the region x1. What's the last time? The answers? Yeah, x1 goes to is less than x2, or you have x a12 I k1 x2 k2 x1 plus a1 e to the I k1 x1 plus a2 x2 x2. So we made that's like this one. Oh my goodness, sorry. It's wrong on this. And if you do the integration around so around the x1 is equal to x2, and then what we have the equation motion is that the where is it? Yeah. So psi function x1 minus function psi function x2, which is the slightly is equal to x2 0 minus function psi function x. and this is equal to 2c psi xy equal to x2. By solving, by just integrating this Schrödinger equation around the x1, and then of course you can swap okay, yes. And from here, and if you plug, so this is called beta ansatz. Or more precisely, this is called usually nowadays called coordinate beta ansatz equation. So nowadays it's called coordinate. So actually, the reason why it's called coordinate is there is so-called the beta ansatz called algebraic. If I have time, I will explain algebraic beta ansatz at the end of the lecture, the last lecture maybe. Okay. Yes. Thank you very much. Thank you very much. Okay, that's the case. And then, so we plug. So this is called coordinate beta. That's this is 1930s. What made assumption. this is bosons. So you can exchange the two particles. So since unless you have the two bosons have the same position, it's just a free theory. Free theory means only kinetic term is present, and then okay. And plug that into here. Plug that this one into here, and what we get is A12 is equal to minus C. I will write a bit different way from last time. C plus I K1 plus K2. This is what you can show, and A21. That's what you can show. Just plug this one into here, and then you can show this is the case. And of course, if you do the opposite side, A21 is equal to minus C minus I K2 minus K1 divided by C plus I K2 minus K1. Okay, so that's the case. So if you plug this coordinate beta that's to the Schrödinger equation, and then you get this relation. Okay. So now we can use the. So last time I don't know which notation I use, but here I use SK1, K2. So scattering amplitude is indeed a ratio between so A12, A21. So just this is equal to minus C minus I K1 minus K2 minus C plus I K1 minus K2. And if you swap so if you swap the coordinate K1, you just have a A21, A12 minus C minus I K2 minus K1 C plus I K2 minus K1. And then, so this ratio, if you use the following relation, so we can just have, yeah. Okay. So this is the case. And then if you, let's see. Yeah. So this is the case. And if you use the, so this, if you use this one is equal to, so if you just write down this one is equal to minus e to the I theta 1, 2. This is equal to minus e to the I theta 2, 1. If you write this one, then what you get is theta 1, 2 is equal to minus 2 times inverse k1 minus k2 divided by c. And theta 2, 1 is equal to minus 2 times inverse k2 minus k1 over c. So you can write like this way. So from here to here, there is a formula, so-called, I mean, you have to do calculation, lots of calculation. I use the mathematical to be honest. 1 plus ix and the exponential minus 2i times inverse of x. That's, if you use this relation, so just plug x is equal to whatever, k1 minus k2 or k1 minus k2. Then you can identify what is the theta 1, 2. You can identify what is the theta 1, 2. So this is a formula. So actually, coordinate Vedanta equation, if you try to solve, you have to use this relation a lot. This relation a lot. And this can be derived by just ordinary trigonometric functions. So, the last time I told you wrong. Everybody looks very tired. So now, so we impose a periodic boundary condition. So which means that the system is the invariant and the x goes to x plus L. So periodic boundary condition. Boundary condition. So then what you get is that the this wave function. So wave function, once you do the phi goes to phi x1, x2 goes to phi x1 plus L x2, then this is equal to e to the I k1 x1, sorry, L1. So you have a phase factor. You just get the translation, and if you do the opposite, x2 plus L, you have the opposite. So from here, one can just show that the A1, 2 is equal to n. So they plug this one. This answer, according to that answer state here, A21 should be e to the I k1 1. So not L. And then you have A21 is equal to A12 e to the ki k2 L. This is what you get from the plug this periodic boundary condition. using periodic boundary condition by using coordinate analysis equation. So now, so you just compare between them. So we know the ratio between A12 over A21 is the scattering matrix. So this is scattering matrix I introduced last time. Slightly different notation. Okay, slightly different notation last time. From last time. Then if you compare between them, so you can just short of the K1. L1, L is equal to 2 pi I1 plus theta 1, 2. K2, L is equal to 2 pi I2 plus theta 2, 1. As you can easily see, this I1 and I2 has to be half integer. It has to be half integer. Means the really strictly half integer. So if you compare between two, there's a minus sign here. Okay, there's a minus sign here. And then if you compare between KIL, theta 1, 2, K1L, and the theta 1, 2, there's a minus sign here. So therefore, there's an overall shift has to be pi times some integer. All integer shift to be there. Okay. Okay. So this is what you get from two particle state. And if you look at this one, and then so if you look at the solution, so if you impose K1 is equal to K2, there is no solution. Yes. Yes.
So these two equations actually solve because they underline the inverse of the other line.
Which one? This equation?
These two.
These two? So these two, I mean, I try to explain. So just plug this one into this Schrödinger equation.
Yes.
Then you get this ratio is indeed this one.
Yeah.
Okay?
Yeah.
And the opposite is just swap K2 and K1.
Yeah, but the down line that's the inverse of the upper line.
Yes.
But if you solve this equations and the upper line equals to the inverse of the down line, you will get K1 equal to 0 or K2 equal to 0.
K1? What do you mean?
I mean, if you solve this C minus this upper fraction.
So this one
yeah.
is equal to this one?
No.
This one?
Yeah, minus the inverse.
Okay.
And you will get K1 0 or K2.
Why? But how do you solve the equation?
You can try. Just
But how do you solve the equation?
I mean, if there's only one equation, but you have K1 and K2, you can solve a relation.
But what is the equation you have?
I have K1 plus K2 squared equals K1 minus.
No. I mean, so you have the which one is the equation? This is equal to this one?
No, this equals the inverse of that.
Okay. But that's too obvious, right?
Yeah. But you can solve it.
What do you mean? But this is equal to this inverse of this one, right? But that's obvious, right? There is no equation. What are you talking about? What do you mean? No, I don't understand the question. No, I don't understand your question. So this is inverse of this one, that's for sure. What kind of equation? What do you mean? No, I don't understand your question, sorry. And if K1 is equal to K2, so if you K1 equal to plug that into here, you just have a -1 here. -1 here. So this, if you plug this one into this equation, you get the A12 is equal to -A21. Okay, -A21, and then so if you plug A12 is equal to -A21 and plug that one to here, and in fact this is will give you the wave function vanishes everywhere. Okay, so can you see that? Let's see. So plug this one into here, so you have the plus. I mean, essentially, you have an overall factor. You have a minus sign, and on the other hand, if you go to the opposite side, you have a plus and a minus sign here. And then what you should have is the, let's see. So why this should be, so let me think. Yeah, so I think it's bosonic. So you have the x1 is equal to x2. It should be should coincide. Okay, should coincide. So here, if you plug A12 is equal to -A2 over here, you get this minus this one. On the other hand, you have a if you plug this one into here, this minus this one, they are the related minus sign, but they should overlap. X1 is equal to x2 region. Therefore, A1. Do you understand what I mean? So if you plug this one, so psi should be some number A12 times E3I K1 x1 plus K2 x2 minus e to the I K2 x1 plus K1 x2. And then on the other hand, if you go to the opposite region, you have K x2 plus K2 x1 minus e to the I K1 x1 plus K2 x2. Okay. And then they should overlap. They should coincide with the x1 is equal to x2. And since they are related by minus sign, they should vanish. So A12 should vanish. A12 and A should vanish. What?
It should be epsilon greater.
Oh. Thank you very much. Should vanish. So this means that if K1 and K2, so this means the psi function should be 0. Okay. So let's do the same exercise for three bosons. So now we will do the same exercise for 3 bosons. Yes. The 3 bosons. And now the ansatz is much more, it's just straightforward generalization. Now, so we have psi x1, x2, x3.
May I ask what the scattering matrix is defined as?
Scattering ratio between.
What this definition means scattering matrix?
So it's a probability when the particle 1 has a k1 momentum, particle 2 has a k2 momentum. So it's A12. The opposite is the particle 1 has a k2 momentum, particle x2 has a k1 momentum. And the ratio between them should be it can be understood as a scattering matrix. You just have the ratio between scattering matrix. The ratio between them. I mean, you can consider as a definition. I mean, whatever you call it, it's okay. I mean, whatever you call it, it's just a ratio between the two probability. You have particle 1 and has a k1 momentum, particle 2 has a k2 momentum, or the opposite. The probability between them can be just called the scattering matrix. Okay, we can do the same exercise. So here, so you have yeah. Three bosons, so we will do the same exercise. A1, 2, 3, e to the I, k1, x1 plus k2, x2 plus k3, x3. Okay, it's boring, but let me do the following. A2, 1, 2, 3 is equal to, you just do the permutation symmetry. E to the, so this is the coordinate beta, that's e to the I, k2, x1 plus k1, x2 plus k3, x3. And then, so of course it's a, how to say, it's just a permute, the 1, 2, 3, how many times you should have in total? 6, good. So another possibility is the A. So order of A3 is 6. Okay. So
Excuse me, I still have a question about the scattering matrix. Generally, the scattering matrix can give the amplitude of the scattering if we project. Then how can we see it from this definition?
So I already erased. So A12 is the particle 1 has a k1 momentum, and particle 2 has the k2 momentum. A21 is the opposite. And the ratio should be the probability between the scattering. What do you mean? So you have the K1 and the particle 1 has a K1 momentum, particle 2 has a K2 momentum, and the opposite. So particle 2 has a K1, particle 1 has a K1 momentum, K2 momentum, sorry. Particle 2 has the K1 momentum. Okay? So this one is called S12 scatter matrix. schedule. The probability between these two is the just ratio between these So what is the no? What is the what is it called? Huh? Order of the SN? Permutation matrix in SN? What is the order? N factorial, good. So N factorial. So you should have an N factorial. And then you just do this, just permutation. So, okay, let me write down. So let's do slowly. A2, 3, 1, E3, I, K2. I mean, okay, it's maybe too boring for you. K1, X3 plus A 3 to 1 E3I K3 X1 plus K2 X2 plus K1 X3. And then you have a two more term. Okay, 3, 1, 2 E3 I K3 X1 plus K1 X2 plus K3 X3 plus A 1, 3, 2 E3 I K1 X1 plus K3 X2 plus K2 X2. In the region X1 is the X2 X3. So this is the coordinate beta on that, and if you go to swap the region, if you try to swap the region, and whatever, x sigma 1, x sigma 2, x sigma 3, where sigma is the permutation matrix, permutation group, okay, sigma, then you just swap x1, x2, x3, and so on. Okay, so that's a coordinate beta on the solution. And now we can do the same. Essentially, what you have is essentially the here I and j and I and j. This is I and j and I and j. So this is the indeed the when they if you do the integral around the xi is equal to xj, you get this condition, and then we do again the similar thing. So we just call the where did I write? Oh yeah. So instead of so two particle states you have this one, but for three particle state you just define A1, 2, 3. So you just select A 2, 1, 3 divided by A 1, 2, 3 is equal to minus e to the I theta to 1. Similarly, A 3, 1, 2. It's very similar to two, just straightforward generalization to three particles. Two particle to three particle. E to the minus e to the I 3, 1, and then 3, 1, and then A 3, 2, 1 divided by A 2, 3, 1 is equal to e to the minus I theta 3, 2. You just define like this way. So theta. Theta. And then So you can also have the similar relation for you. So I just permute the two indices in the first two indices. You can do the same thing for the last two indices. So then you have A 1, 3, 2 divided by A 1, 2, 3 is equal to minus e to the I 3, 2 A 2, 3, 1 divided by A 2, 1, 3 is equal to e to the minus I will miss minus sign I to the 3, 1 and A 3, 2, 1 A 3, 1, 2 is equal to e to the minus e to the I 0, 1, 2. So this is the swapping last indices. So now so what we have is that the so here you have a 1, 2, 3 particle, and then I think it's a famous Yang-Baxter relation. So 1, 2, 3 is equal to this one. 1, 2, 3. So you should have this relation. Okay. So which means that the so this one is so here this one is equal to A1, 2, 3 is equal to A 2, 1, 3, and then you have A 2, 3, 1. Oh, I don't have a space to write down. Sorry. I have A 1, 2, 3, A 2, 1, 3, and then now A 2, 1, 3, and this one is the A 2, 3, 1. So you just swap 1, 2, and then now it's swapped by 1, 3. 1, 3 is swapped, and next you have to swap this one, which means A 3, 2, 1 is equal to the same as here. A 1, 2, 3 goes to A 1, 3, 2, A 3, 1, 2, and then A 3, 2, 1. Okay. So first you swap the 2, 2, 3, A 2, 3, and then next you just swap 1, 3, and then you swap the 2, 1. Okay. The opposite so this is some precursor of Yang-Baxter equation, and this will give you A31. The ratio between 3 to 1 divided by A1 to 3 is indeed equal to e to the minus. I already missed the minus sign. Theta 2, 1 plus theta 3, 1 plus theta 3, 2. And this is indeed equal to S K2 K1 S times S K3 K1 and times S K3 and K1. So this is the scattering aperture, multiplication scattering aperture you have. So this is the 3 particle state. And then again, so you just try to solve the ratio between, if you impose periodic boundary condition, A 1, 2, 3 divided by A 2, 3, 1. So if you just the periodically swap the indices, so then you have e to the I K1L. So you should have K1L. So which means that you just have the particle 2, 3 And but you just do that coming back to the so you have particle 1 and you just swap the order. So there's a boundary condition. 1, 2, 3 equals to 2, 3, 1. 2, 3, 1. Okay. That will give you just a translation of K1 momentum by L. So the same thing happened for the other part. 2, 1, 3 is equal to A 1, 3, 2 is equal to, you just permit the indices, you have I K2L, and then you have A 3, 1, 2 divided by A 1, 2, 3 is equal to E to the I K3. So this is the 3 particle generalization of 2 particle to 3 particle. Oh, thank you very much. I often make a mistake in the indices. This should be 3, 2, maybe. 2, 1, 2, 1, 3, 1, 3, 1, and 3, 2, 3, 2. Okay. Thank you. Thank you very much. This is a relation. Now, so you just compare between these two. Okay. And now, so since I also miss minus sign here again. Minus sign here, minus sign here, minus sign here. And now, so if you compare between the relation between the difference between 2 and 3 boson is indeed you have either minus sign, but here there is no minus sign. Okay. Okay. So therefore, what you can do is that if you compare between these two, one can just conclude that the IK, so K1L is equal to 2 pi I 1 plus the theta 1, 2 plus theta 2, 1, 3. So that's, you can see from where? So this is indeed equal to, 3, 2. So this is 3, 2. Sorry, I think I really messed up the, this should be 2, 1, sorry. 2, 1. Okay. This should be 2, 1. Okay, so let's see how to get this relation. So this is a ratio between A1, 2, 3, A2, 3, 1. And this should be given by, how do you get this relation? So A1, 2, 3 divided by A2, 1, 3. And you have A2, 1, 3 divided by A2, 3, 1. Okay, do you understand what I mean? So this ratio is given by these two products. And you plug the relation over there. You have a theta from this factor. You have a 1, 2 factor, theta 1, 2 factor. This factor you get the theta 1, 3 factor. Okay. But since now you have multiplied 2 factor, minus sign cancel. Okay, 2 minus sign cancel. So therefore I1 should be integer. So that's the difference. Okay, 3 particle states I1 should be integer. You understand? The two particles state, if you consider 2 particle state, I1 should be half integer, right? Plus 1 half. You used to have this one. You used to have this one, but now you don't have this. And similarly, so you can just swap the indices. K2 L is equal to 2 pi I2 is 2 pi I3. And now, so we just the 2, 3 and the theta 2, 1. So this is what you get. And then you have Seder 3, 1 plus Seder 3, 2. So this is what you obtain from the relation. Okay, so that's what you have from the straightforward generalization of the two particles of two bosons, two bosons to three bosons by using this it's called coordinate beta analysis. So you just the beta assume the wave function is a linear combination of plane wave and plug that into the Hamiltonian, you get this. And we all know, so two particles, anyway. And I already erased, but as you know, so theta 1, 2, theta ij is indeed equal to -2 tan inverse of ki minus kj divided. So this is the relation. So in two particles, so we already derived this one. Theta. Do you remember? I already erased, but if you take a note, you already have this relation. So so here this is coming from aij is equal to minus c minus I ki minus kj divided by c plus I ki minus kj. This is we call e to the minus I theta ij and then theta ji. Okay. So this is two particle states coming from. I mean, it used to be I is equal to 1 and j is equal to 2. Okay, I equal to 1, j equal to 2. But anyway, straightforward generalization just reply. Okay. Any questions so far?
I ask how this is related to the Baxter equation?
So this one is not Yang-Baxter yet. This is not it's just precursor of Yang-Baxter. So you just have the you have from 1, 2, 3 to 3 to 1. You have a two way to go to from A1 to 3 to A3 to 1. Just try to mention. But anyway, so Yang-Baxter is much more complicated. It's just a scalar multiplication you just multiply e to the I theta. So it's just a scalar multiplication. So it's not the deep thing. It's just scalar matrix. So later, so this e to the I theta becomes matrix. So then it becomes Yang-Baxter. I just mentioned the precursor of Yang-Baxter. Okay. Yeah. And of course, energy here, even energy of any boson is sum over ki where I runs for 1 to n. Okay. 1 to n. Okay. And then you just plug. So essentially what you need to do is that so here you need to solve this equation. You need to solve. So in two boson states you have K1 is equal to pi I1. Sorry, K1L plus theta 1, 2 as far as I remember. yeah, K2 L is equal to pi I2 plus theta 1. So you have a, this is free particle states, and plug this one into here, and given that I1 and I2 are the half integer, strict half integer, and plug this one into here, and you need to solve the you need to solve K1 and K2. So this, you have a two variable K1 and K2. So given a so I1, I2, so this I, so I whatever J is called quantum number. So often called beta quantum number. Beta quantum number. Okay. So given a beta quantum number, and just so you have a given some half integer, and plug theta ij into here. So you have a two unknown variable k1 and k2, and then solve the two equation. You get the k1 and k2. Okay, you should get the k1 and k2, and plug down into here. You get the energy of the system. That's how you solve this delta function. It's a similar thing here. So given a quantum number I1, I2, I3, you have a two unknown variable K1, K2, K3, and plug this one into here. You have a three unknown equation and a three equation. Okay? Essentially, you can solve the equation, and then plug down into the energy. You can determine the system of the energy. The energy of the system. Okay, that's how you solve the. And now, so we just solve the system by two bosons, three bosons. Next is n bosons, and which I didn't. Yeah, I mean just doing. Yeah, last time I just going to rush, and then my explanation too bad, so I just try to be slow this time. So let's go to n bosons. And beta ansatz is very simple. So beta ansatz is indeed psi of x is equal to sum of p. P is the permutation group with the n, order n factorial. P is equal to a kp dot x. Yep. Kp of, well, more precisely xi, and I call it xi. Xi is really region like a 0, or maybe last time I call it q. Sorry, I call it q last time. Region, and xq1 is greater than q2, and x to n, and then so you understand what I meant. So I mean, I'm not gonna write down. So you just have a a1 to and e to the I k1 x1 plus plus k n xn and plus n factorial term. Okay, so you understand what I meant, right? In the region between 0, x1, x2. I try to be very pedagogical today because my preparation is very weak today. So you have the n factorial term. Okay, you understand? You just swap k. Okay, yes. But if you go to the different region, you start with different region 2 and 1, and you start with 2 and 1, 2 and then 1, 2 and 1, and then you just swap all the momentum k. Okay? So this is coordinate beta ansatz. So this is called coordinate beta ansatz. That's what the beta did. Ansatz. And then we can solve the similarly. So then what we would have is indeed if you so for instance you just have if you have 1, 2, 3 n is equal to minus, so you have a very similar relation as before, I k1 minus k2 divided by c plus I mean, just do for pedagogical, k1, k2, 1, 3, I mean, okay, let's go to write down 4. Okay. 4, n. Okay, this kind of stuff. So relation between two amplitude is related by this factor, simple factor. Okay, only like two indices. If you permit two indices, you get this factor. Okay, that's same as two boson states. And you just have a multiple of the case. Okay. So yeah. So if you have more generally, so if you have the a 1, 2 I plus 1 n, so you have 1, 2 I plus 1 I n should be, this becomes I and the I plus 1. And this is the I plus 1. Oh, sorry. It's okay. I plus 1. Okay. So this is what's going to happen. The two amplitude. Now, so we can have the similar relation. So if you have a 1, 2, 3 n divided by, yeah, there's the same relation as before. A 2, 3 n1 is equal to e to the I k1 l. Okay, you have the opposite. So you have bunch of 2 to n, and one particle is go to, so particle 1 goes to 0 to n, and periodic boundary condition. You have a, it used to have 1, 2, 3, 1, 2, 3 to n, but now you have a 2, 3 n1. Okay, that is given by the factor is just translation between from 0 to L by momentum k1. Okay, so that's what you get. Okay, that's what you get, and then here. So therefore, what you have is e to the I k1l is indeed product of j, which is not 1. Minus c minus I k1 minus kj divided by c plus I k1 minus plus k kj. This is product. Okay, so do you agree? So you just do the multiplication one by one, okay? Scatter matrix. Do you understand what I mean? That's what I tried to convey last time. I'm being very slow. Sorry. 1, 2, 3, 4. Okay. So therefore, instead of 1, sorry, my indices maybe looks very confusing. But if you change 1 to whatever I, it becomes ki and ki. K minus. Okay. More precisely, and this one can be written as -1 to the n minus 1, and the product of exponential of I times sum over sum over j is not equal to I, and the theta ij. The opposite, yeah, this is correct. So this is what you have. Is it okay for you? So theta ij is exactly over there, here. So as I mentioned, this to get this direction. So of course you need to take a log of this one, But I mentioned many. To solve this coordinate Bethe-Ansatz equation, you have to always use this relation: 1 minus ix, 1 plus ix. I check this one by mathematical, actually. Tan inverse x, as far as I remember, x. You have to use. Actually, this one derive. You can just define derive. Tan x is equal to whatever x minus. No. E to the I x. Okay, I think it's right. It's better to write better. Tan x is equal to e to the I x minus e to the minus I x divided by ex plus e to the minus I x. Sorry, okay. And use this one. You can derive this one by hand, actually. It's a good exercise. I just confuse myself a lot of times, but you can derive. It's a good exercise. Okay, if you're motivated enough, you can just do by yourself. Okay. Okay, good. So now, just try to solve this equation. Unfortunately, I don't have. Well, let's erase this controversy. So this equation will give you KIL is equal to 2 pi, again, I, small I, plus sum of j is not equal to I, theta ij. Okay. So this is the equation. And this the Bethe quantum number I is indeed half integer if n is equal to odd. It should be integer if n is equal to even. Okay, n equal to even. So that's you can see from. This quantum number I coming from this factor, really this factor. When n is equal to odd, yeah, I think if you use this relation, you have a minus sign here. Yeah, it's cool. Huh? Sorry, it's the opposite. Sorry. Oh, why am I so stupid? Sorry, it should be opposite. Okay, it should be opposite. Yeah, sorry. So if n is odd, it becomes 1, right? It becomes 1. So therefore, it should be integer. If it is n is even, so it gets minus sign. So therefore, it should be half integer. Okay, strictly half integer. This is what happened, right? So when n is equal to 2, it used to be like a half integer. N equals 3, you have an integer. Okay, sorry. Okay, and now plug. So given the Bethe quantum number, and plug this into here, you have an unknown variable, ki, but you have an equation, okay? An equation, so you can solve it. And to determine E is equal to sum over there. It's already written me. So the energy of the system is just is equal to sum over ki squared. So just solve this equation and then plug that into here. You can determine the energy of the system exactly. Any question? So this is the coordinate Bethe-Ansatz equation in the one-dimensional and bosons and delta function. Any questions so far? And then we will move on to Heidemann spin chain from now.
When we solve these equations, how do we choose the I
I0?
how do we choose I? Since it is
This I?
yes.
Okay, so that's good question. So that's good question. So let's move on to the two-particle state in that case. So it depends on so this energy really depends on the choice of I1 and I2. Okay, so I1 and I2. So therefore, you have to solve when the ground state fine. So when you choose, okay, good question. So this energy really depends on the choice of Bethe quantum number. Okay, Bethe quantum number, and then so as far as I understand, if you pick I1 is equal to I2 equals 0, you cannot solve this equation. As far as I understand. So let's try to write down. So if I1 is equal to I2 is equal to 0. So physicists can guess. Looks to me this guy, sorry, so this has to be half integer. So let's solve this one. It has to be half integer. So then it should be K1 L is equal to pi L. So pi, it's just pi. Just plug that into here, you get the pi plus over there minus 2 tan inverse K1 minus K2 divided by C. K2 L is equal to pi minus 2 tan inverse K2 minus K1 over C. And then, as you can easily see, for instance, if you take an extreme case, C goes to infinity. C goes to infinity, K1 is equal to K2. It becomes K1 is equal to K2. And we know wave function vanish. That I already explained. Okay. And then for generic C, I'm not sure this has a solution, to be honest. I don't know. I never solved this, but I don't think this has a solution. And then I'm pretty sure that the ground state should be I1 is equal to 1/2, I2 is equal to minus 1/2. I think this should be ground state. This should be ground state. And then the excited state is more like a 3 and whatever, pick random half integer, you get the excited state. And so on. This case, if you're motivated enough, you try to solve this equation by using the Bethe-Ansatz, coordinate Bethe-Ansatz I already written there, if there's a solution. I think this doesn't have a solution. Yeah. But the ground state is the 1/2 and the minus 1/2. Minus 1/2. And then excited state is just pick arbitrary half integer and you get the excited state. Any other questions? Okay, let's go to Heidemann spin chain. So I just first explain what is a Heidemann spin chain, and then we will take a break. Okay. Can I erase this part? Yeah, this is 3 portion. Okay. Okay, so let's move on to Heidemann spin chain. This is not what I want. Where is what I want? Yep. So Heidemann spin chain is the following. It's very similar to what you have solved in the okay, let's write down Heisenberg spin chain, or often called XXX spin chain. And Hamiltonian is just given by minus J sum over n Sx n Sn plus 1 x plus Sn y Sn plus 1 y plus Sc n Sn plus 1 whatever. And so we just have again periodic boundary condition. You have an n site, whatever spin, one half state. So and each side you have a plus minus one state. Okay? Each side you have a plus minus one state, spin up, spin down state, and of course s whatever x s. Which symbol which I should use? Whatever x, y, z, x, I is equal to power matrix divided by 2. Okay? Divided by 2. Now sigma is power matrix divided by 2 is x. So this is Heisenberg spin chain. Yeah. And this can be written as the, of course, is equal to minus j over 2. Sum of n is the Sn plus 1 minus plus Sn minus Sn plus 1 plus 2 Sn c Sn plus 1. Okay, so this, and of course you have Sn, whatever, the plus minus is Sx plus minus I Sy. Okay. So this is it's just the ordinary quantum mechanics. Ordinary quantum mechanics, and this is Hamiltonian. Okay. So this is Heisenberg spin. And we want to solve solve means we want to find what is the momentum. Okay. Momentum of the average of momentum P, or what average energy E. We want to exactly solve, as in the delta function model. And the ground state either, what was the choke? The ground. What is the ground state? The ground state. So what is the ground state in this system? Huh?
Is J positive?
J is supposed to be positive. Good. So you have two ground states, either all spin up or spin down. Okay. And so which means so you have plus. So this is or the minus. Okay. And on purpose, for the sake of it's okay, whichever you think about. So let's pick this guy, okay, as a ground state. First, what is the first excited state in that case? Okay, you just swap one of them. Okay, so this is first excited state. Okay, the ice one.
spin one half because it's probably gapless. We cannot make the first exciting state.
What did you say?
I don't know.
Mm-hmm.
I think this system is gapless and which cannot make the first exciting state.
Why?
The spectrum should be continuous.
Why is the spectrum has to be continuous? Why?
Because
Why do you think it's continuous?
the spin can rotate on an acid on a lot, so it can slightly deviate from the original position and
Mm-hmm.
can rotate infinitesimally so that the excited state can be infinitely close to the one state.
Oh, I see. So you just have the I see. So it's so here. So you, instead of just plus or minus, you just have a linear combination between these two.
Yes.
Good question.
So this means this model has a ghost mode.
What do you mean ghost mode?
So it's like if we have the spins, so we can rotate it infinitesimally. It's actually the same thing as set.
Good. Okay. Good. I think you made a good point indeed. You made a good point. Let's see. So you just want to consider the linear combinations these two. That's totally fine in quantum mechanics. That's totally fine. Good point. And that's what I'm going to do from now. We will consider linear combination of this one. That is actually better understood. Okay, so I shouldn't call this first excited state. Sorry. You're right. It's called one magnum state. Okay. I should call it one magnum. One magnum is one of the spin is going down. Okay, thanks for. So I shouldn't call first excited state. So one magnum state, so which is just swap the one of the spin to the down. Okay. Spin to the down, and then of course it's a fermionic state. It's a fermionic system. So two magnums. You have plus. I mean, where's the minus? There's some minus sign, and the minus sign. The rest of it is plus. Okay. And so on. And this is exactly very similar to what we have considered in delta function states. So you have any particle, so here this looks like a two bosons, or like two boson states. But here you cannot occupy the same position, right? It's a fermionic, so you cannot have you cannot collide at minus sign. So therefore, it looks like a delta function. Even though you just move this minus sign, you cannot have you cannot. I mean, if you occupy this, if you collide, it goes back to one magnum state, which cannot be done. Okay, so therefore you can treat this system look like the Hamiltonian with delta function, and then so what Bene did is indeed. What should I write? Okay, so I think After the break, I will talk about one marginal state, how to solve one marginal state, super easy. And then next is how to determine the spectrum of the two marginals states, and how to determine the energy and the momentum for two marginals by using beta ansatz. So essentially what we are going to do is indeed for two marginal states is the whatever wave function is indeed sum over f n1 and 2, sum of n1 and 2. N1 is not equal to n2. So n1 and 2 means that the position of n1 and n2. Okay. So it's 1, 2, total n1, and minus sign appears for n1 and n2, and you just consider linear combination of them. Okay. And here f again we use the beta ansatz. So you just have some ai, so whatever a1 2 e to the I k1 whatever n1 plus k2 n2 and plus a to 1 e to the I k opposite. You just swap k1 and k2. I'm not going to write down. Maybe I should write down plus a to 1 e to the I k2 and 1 plus k1 and 2. So that's what we are going to assume after the break and try to solve the system, the spectrum of Hamiltonian. Exactly. Okay, let's take a break.
它是哪里？我觉得有这么强的人应该有。
那个东西，你可以把它那个角度放进虚的就可以。
修单元过了呀。
不会啊。
这是相当简单。
对。所以
这是什么？
这是一个科学有关对称性有请求的东西，把它要子。
哦，就是它不能这样子朝上。
它本来是可以在整个和球面上，现在只绕着一个整个。
绕着这个
然后它的一个，就是看这个动量，看这个波的动量是，这个动量应该不能记。
那它一定会形成一个波吗？
但是如果你是奇奇怪怪情况下，是这个分裂分解成，
好像是这个上午上，应该是。
为什么它一开始可以在整个上升，但现在变成全让一根整段就两条去了？
Which was
This is Professor Zhang Xiang's lecture notes on quantum mechanics.
he teach this one?
No, he teaches about magnet. And this magnet is not this magnet.
Oh, yes.
It's not the same thing.
因为这样子理解，因为这样子。
没有，就是它本来应该是去年学的样子。
刚刚我
但是我没有
刚刚手动体验过去这样子。他在伯克利，在伯克利有线上的 poster session， 然后里面你可以像那个小人，就是。
It's quite amazing. So at the end of the day, so only like 4 grad students are here. Even the rest of students, I think 15 graduate students. Okay, they became lazy.
所以你
所以它已经完全搞成线上。
没有 Steven Louis 李东海。
Yes.
I have some question about CFT. So, can we describe any phase transition by CFT? So if it is a 2D.
一开始绕着整个球段，现在变成一根整段这样。
What do you mean phase transition?
In the phase transition point, can we write any model in 2D and describe it by some kind of CFT?
I mean, this phase transition, the phase transition point is called critical point, and the critical point is, should be described as CFT.
So if we write a model, it has a phase transition, we can describe it by CFT.
At the critical point. At the critical point.
Oh, okay.
Critical point you can describe.
And in the previous maybe the master we calculated some model like a Ising chain with long range interactions such as it can decay algebraically power law or maybe.
Which one are you talking about?
So just like this. So
which model are you talking about?
Ising model. And,
Okay.
The interactions. So the J, maybe the J, is depend on the coordinates. And just like this one.
Okay.
So it is a long range model, and so I'm thinking about can this model find some safety to describe it?
What is J?
The coupling constant. It's not a constant. The coupling between the neighbors. So it is not a short range coupling. It's a long range. So it decays.
You mean 2-point function?
2-point function? No, it's just J. It's just,
But J is given, right? Already.
yeah. J is given.
But how can it be depends on R?
It's so we have 2 points and they interact with each other, and their J depends on their distance.
Why? But Hamilton is already given, so J is fixed.
No. So we write this model. So.
It means the coupling constant.
Yeah.
There,
And R.
this I and J are not nearest neighbor. They can, their distance is called R.
Okay.
And the coupling constant between those two spins is JR. And JR is a function of R.
Okay.
So this is called a long range Ising model because
Okay.
those spins has a long range interaction.
Okay.
with each
Okay. Okay.
And if this long range interaction is strong enough, then the dimension of the if this is very strong, then a one-dimensional chain can be effectively collapsed to a 0 dimension because the interaction is so strong. So that.
Okay.
So your question is.
So my question is, do you see any safeties like this can describe these things?
I have no idea.
We did a project together. I along with
Okay.
Xinyu, we calculate the critical exponents of this
Okay.
model
Okay.
in 2-dimensional.
Okay.
So at the critical point, maybe there is some kind of CFT describing this.
I have no idea. I have no idea. But critical, if it is critical point, is there a chance? Is there some CFT? I don't know which one it is.
Actually, the phase transition
Mm-hmm.
in this model is KT phase transition.
KT? What's KT?
Constant.
Sorry. I see. I don't know what kind of CFT that described at the critical point. But it becomes gapless
Yes.
at the critical point.
It is gapless near the critical point.
Oh, okay. Then most likely it'll be described as CFT, but I don't know what kind of CFT it is.
Okay.
Is there a method to figure out which CFT describes?
I'm sorry?
How to figure out the event of the critical point? Is there a method to find out which CFT describes?
Can you find the first of all? Can you find the central charge?
How do you define? I don't know how to calculate the simple charge.
No, for instance, if you put the system in the finite size,
Yes.
the cosmic energy is central charge.
I see.
So I already forgot. C over L, some number, 24, I forgot.
I see.
So that is, if you put the system on finite size, the cosmic energy should be proportional to central charge.
People also calculate the entanglement entropy and the field.
Yeah. That is one another way. Yeah. Good. That's a very good question actually. This is the best question I ever received in this class. Okay. Shall we resume? So I told you the Hamiltonian with any particle, so it's now becomes this course becomes particle physics. So no need to excuse to this difference. I already taught him particle physics today. Okay, so let's first solve the von Magnum. So undergrad students are always here. Yeah, I know the undergrad students here is almost like a selected, almost top class students in this generation. Grad students only 1, 2, 3, 4, 5. Okay, 5, 6 maybe. 6 out of registered students. But anyway, so I just want to have students who want to understand and listen to my lectures. I don't care the number of students. Okay, so let's solve the von Magnum. Then try to understand the spectrum of the linear combination von Magnum. So linear combination von Magnum can be understood as some proportional factor sum of k. N. So I call it Z over LZ. Z over LZ is a site. L is a site. So 1, 2, 3, ... to L. Okay. So Z over L is just a periodic. It becomes periodic. Do you understand? You understand, right? So you have an integer, but if you quotient by LZ, you just becomes like this. Z over LZ. Good. And then you have a linear combination I, K, M, and N. N is indeed, I call this is N is equal to, and this is N1. I call. So try to solve the system. And Hamiltonian over there, here, Hamiltonian is written over here. And we know that the S plus N, Sn plus 1 minus acts on M, N is equal to, what's going to happen? I should go N, sorry, N, because, so what's going to happen? What's going to happen this one?
N minus 1.
Huh?
N
Why is that? Why is that? You mentioned n plus n minus 1, n plus 1. Why this is the case?
Because it turn over the speed on m plus 1 to the minus side. And
Good. So, I mean, so as you know, so if you have a plus and acts on as plus is always 0, right? Always 0. It's a raising operator. So therefore, this S plus, unless it hits minus signs, it effectively do nothing. It just gives you 0. So when n is equal to m, it does spin minus to spin plus. Okay. But this guy will go to spin plus to spin minus. Okay. Therefore, you have a plus 1, m plus 1. Okay. Similarly, so this is the first term, and we need to go to the second term. So you have s minus. So what is? Good. And then. So what is this? What's this? So what's this? So as you know, if the spins align, and s whatever. A line which acts on z and z, and then this is n plus 1, n, this is equal to 1 quarter plus plus. Okay. On the other hand, if you have plus and minus or minus plus acts on this guy, Sn z, Sn plus 1, sorry, n plus 1, z, you get the minus quarter, whichever. Plus minus plus. Okay? That's what you get. Okay. Therefore, this guy is equal to indeed JL over 4. So the energy is the ground state should have this one. Okay? So J is the Kaplan constant. The quarter coming from the L copy of quarter will give you energy. So here, since one of the side is the negative, so therefore here this one should be L minus 1, L minus 4 divided by 4. Sorry, I call it M. So sorry, this is Z. Can you, do you understand why? Do you understand why? So difference between, so from here to here, you need to go, you need to add, energy essentially 1/2, okay? But you have plus dot plus minus plus dot plus, right? And here you have the energy cost is 1/2 and 1/2. Okay, so therefore in total you need 1. Unit 1. That will give you this one. Okay. So therefore, if the Hamiltonian acts on, okay, let's normalize minus 2 over j. 2 over j acts on this psi k states. Then what we get is the essentially square root L sum over n e to the I k n n plus 1 plus n minus 1 plus L minus 4 divided by 2. So the 2 coming from here. So 2 is here, so you have to multiply 2 here. Okay, and you get this one. The other side. So the first time comes from this guy. The second time, the third time. Okay. And then just reordering this one, this can be understood as, so it's a periodic. So this can be understood as n e to the I k n minus 1 plus e to the I k n plus 1 and plus L over 2 minus 2. So it's a secret, you just do the shift. So this will give you oh, I'm sorry, I think I should write down like this way. E to the I k n. Okay, so that's what you get. And this is independent of n, so this is energy, essentially. Okay. And this is equal to 2 cos k minus 1 plus L over 4. L over 4. And then, so as he mentioned, so this is indeed, so therefore Ek minus E0 is equal to J times 1 minus cos K. Cos K. So one magnon with the momentum K, one magnon with momentum K will give you the energy here. And as he mentioned, this is a big plus. K can be any plus. Okay. Yes.
So why there is a L minus 4? I think is why isn't it L minus 2?
So I told you, so this pairing give you 1/2. This will give you 1/2 energy cost.
Why is this 4 1?
From 1/4 to minus 1/4. So let's go to the linear combination of 2 magnon and assume this. Assume this. And it's going to be a tedious computation indeed. It's straightforward. But I have to explain in the. It takes half. So we should do the same. So we just assume the linear combination of 2 magnon, and see the spectrum of the
Sorry, I think there must be some story in the relation because at first you assume there are 2 discrete margins, but at last you got the Laplace result. At first, margin.
Because I just considered linear combination. What do you mean? It's a linear combination of magnon. One magnon. Linear combination of one magnon will give you the energy. It's not the single magnon. It's a linear combination of one magnon. Okay, so now we go to the linear convention two magnons, and so there is a how to say L two whatever this way of choosing. So the dimension of the Hilbert space of the two magnon is how to say 2 out of L. Okay, so the choice is so the dimension is L minus 1 divided by 2. Okay, so Hilbert space. Here they will consider the linear combination of this one. And we did the same thing. So you just apply the Hamiltonian on these states, and what's going to happen? Okay, it's tedious, but we need to do. So if you encounter some problem, physics has to do explicit calculation. Unfortunately, that's our job, even though it's very tedious. And I'm going to do how. So I have at least half an hour. I can finish this two magnon state. So let's consider plus and okay. This. So what's going to happen is what? So can you tell me what's going to happen? I already read the cases already. I already give you some hint. So it depends on how we align. So if it is the case is minus minus plus plus plus, this is a case. You can hit this one. Only so if this hits into this guy, okay, this guy it makes some non-trivial contribution. Therefore, it becomes m1 and 1 plus 2 whatever when m2 is equal to m1 plus 1. So you agree? And otherwise, you have m1. I mean, just usual I'm not gonna repeat. You guys understand. I mean, so this case is otherwise plus minus plus dot 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 plus minus plus dot dot. Okay, and then you get this one. Otherwise, oh sorry, I think it should be minus plus minus. I think I shouldn't write down plus minus. Now I have to be careful about the convention. So which means the m1 is minus m2. Minus case is this one. Then if you hit this one, you get this one. Then I think it should be like this one, I guess. No, sorry. So this is case, and if it is m2 is equal to m1 minus 1, what's going to happen? So then it should be.
Why not assume m1 is bigger than m2 when you define the state?
So it's fine. That's also fine. Okay. Okay, it's periodic. That's also one way to define. Okay, good. Okay. So it's periodic. So we can assume m1 goes to m1. Okay, then so we can do the similar thing. So sum of n minus Sn plus m1 m2. This is equal to m1 minus 1. M1 plus 1 when the M2 is equal to M1 plus 1. So here again, so you have minus minus plus plus, and it only makes sense when this hits to this guy. Okay, so therefore M2 stay the same. Yeah, M2 stay the same, but this guy goes to backwards. Okay, and otherwise you have again the same thing. M1, M2 plus M1, M2 minus 1, and otherwise. And then okay, and then sum of n again is the same thing. Sn z, Sn plus c, n1, n2, and again this is cases. Of course, L minus 2 divided by 2 minus 1 plus L minus 4 over 4 minus 1 acts on m1, m1 plus 1. M1, M2. So here M2 is equal to M1 plus. So do you understand what I mean? I don't know why this note is written like this, but do you understand how to get this one? I mean, okay, here I understand it. Yeah, so if you have plus minus plus dot 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 plus minus plus, you have minus 1 and a minus 1, and that will give you here. And if you have plus minus minus plus, you only have a in total minus 1, right? In total minus 1. I think I should I don't know, it's a bit I mean, let's see how it affect my discussion later. It doesn't affect anything. So I think I don't know why I have written like this. But, I'm sorry, I think I shouldn't write it like this way. L over 4 minus 1, L over 4 minus 2. I think that's what I should write down. But yeah, sorry. Okay, this is the case. And now, here, okay, and then so how the Hamiltonian acts on this oh, I already read the linear combination or coherent states, I would say. It's yeah, I mean it's coherent states. Yes, I mean yeah, sorry. I'm not honor physicist, so I'm not honor physicist, but this is called coherent state indeed. Usually this linear combination, like coherent state. And then here we now assume Fn1, N2, N1, N2. So that's also coherent states. So this is coherent state we are looking at. This is, I call it whatever, psi, maybe. I call it psi, and then let's act the psi a Hamiltonian. So psi acts on like this way. Okay, so then we can do the yeah. I think so. This is the correct way. This is correct way. I just wrote the over 2. This is typo last. So you should correct. So this guy is equal to sum of n2 is n1 plus 1. So f n1 n2. And then I'm going to erase coherent states. And then so we just first pick the above case, okay? Above case. Sorry. No, lowercase, sorry. Lowercase. Because I assume n2 is just greater than n1 plus n2 or 1. And then you just pick the upper and low, a lower case, okay? And then you just do the calculation. I mean, it's boring, but you have to do. And 1 minus 1 and 2 plus and 1 and 2 minus 1 plus n minus 8 over 2 and 1 and 1 and 2. Okay. And plus, it's boring, so it's just and we pick uppercase. And then f n plus 1. You have to do the calculation. To be honest, yeah. It's 4 divided by 2 and plus 1. So this is how we act, and we just really manipulate again. Doing lots of shift and so on to try to find eigenenergy. Eigenvalue of this Hamiltonian. Okay, so let's do the shift. Okay, it's going to be just calculation again. Yeah. When I teach CFT 1, I just give you lots of integral and so on. The similar thing I'm going to do. So, how did you teach QFT 1? When I teach QFT 1, I just do the Heidemann trick and so on. Several students here already took all my QFT 1. I don't think professor cannot avoid this kind of computation. But anyway, so let me do that. So n2 and 1. So just shift one by one. So it shift. Oh my goodness. What I'm reading here is this should be n2. Okay. N2. And everything is okay, right? The rest I just pick up stairs. So you just shift one by one. And 1 minus 1 and 2. So it's boring, but yeah, one class to do. So just bring everything to n1 and 2. Oh, yeah, and plus sum of n2. We have to do this kind of stuff. And plus sum over n2 and 1 plus l minus 8 over 2. And then he just sum over the n1 and 2 and 1 and 2. Okay. And then you just stay as it is. Here is just n. Just leave it as it is. Unfortunately, you have to do it. So this line is just same as this line. So let's leave it as it is. Okay. Now let's do furthermore manipulation. If you do the further manipulation, you will get the following. Let me go to here. Maybe just do them. And this is equal to sum over n2. Shouldn't you explain the Feynman parameter and so on already? Yeah, Feynman parameter to the integral. Okay, do the one loop integral and so on. Okay, good. So then you just pick this coefficient, but you have to be careful about this. I mean here the condition here. But this condition just can be cancelled with this guy indeed. Anyway, let's forget about the CFT one. Okay, so this is the case, but so now we don't increase when n2 is equal to n1 plus 2. Okay, this one doesn't include n2 is equal to n1 plus 2. This one is also same. Okay, and here it includes n2 is equal to n1 plus 1. Okay, and this is the case also. You have to be careful about. So you have to compare with this guy, and then what you get is indeed, I mean this you can do the calculation. It's not so difficult. F n minus 1 plus n plus 1 plus f n plus 2 minus l minus 4 and 2 f n 1 plus 1. Okay, that's what you get from the I mean, so you just be careful about the condition here, and compare with this one, you get this. I mean, it's not so difficult exercise. You can do it by yourself if you're interested. And now, so here we're interested in the states, eigenstate, h hat psi acts on e psi. Essentially, this states we're interested in. So then from here, you will get the condition that the e minus e0 is equal to j over 2 for f n1 and 2 minus f n1 minus 1 and 2 minus f n1 and 2 minus 1 minus f n1 plus 1 and 2 minus f n1 and 2 plus 1. Yeah, therefore that's it. n2 greater than n1 plus 1. On the other hand, e minus x0 is equal to j over 2. 2 times f n plus 1 n plus 1 minus f n plus 2 for sorry, I think I made a mistake. I lost overall factor, sorry. So here, E minus V0 times F and 1 and 2, E minus V0, F and N plus 1. This is a condition which you can easily see from. So these first 4 factor will give you these 4 factor, and then since we have some term proportional to f and 1 and 2, so you just have the minus 4 will give you 4, and here minus 2 will give you 2 here, and so on. And this last time will come from this guy. These 2 guys. Okay, so we want to solve this equation, and to do that again, coordinate beta will appear. Okay, coordinate beta will appear. So coordinate beta, coordinate again, beta ansatz. So this is really what Beta did in 1931 in Heidemann spin chain. So he assumed A12, I1, N1. K2, A21, E to the I, K2 plus K2, 1. So let's assume this one. So this is the answer. So you assume. And plug that one into here. Plug that one there. And plug this one into here, and what you get is as follows. So E minus E0 and 1. I mean, one has to do this kind of calculation. I mean, I don't want to skip this kind of calculation. So then J over 2 4 times A1 2 E to the I K1 plus K2 and 2. But I mean, this and 2. So this is coming from first term. Second term minus. Okay. I'm not gonna write down everything. E to the is the same piece, but you have a shift. You have a shift now, so therefore minus I K1 plus A21 E to the is the same piece, but you have a shift coming from here, which means E to the minus IK2. Okay. Okay, let me be friendly to you. So I call it this yellow guy, yellow, and then blue as a blue, and do the same thing. Many this way minus. Oh my goodness, how many terms do you have? You have 4 terms, right? I need to squeeze into 4 terms. I think I should write them this E to the I yellow, and then you have E to the I K1 coming from. Okay. coming from this shift plus A to 1 E3 I blue E3 I K2. Okay, so blue 1, 2, and now you have A1, 2 E3 I yellow E3 minus IK2 coming from this shift. And plus A21 E3I blue E3R minus IK1. Okay. So minus A12 E3I yellow and the E3. So important part is this one actually, as you already noticed. I should write them more carefully. 2 and this is 2 and this is 2 and 1. So as you can easily see, this one K2 plus A21 E3I here blue and E3I K1. Okay, finally done and done. As you can easily see, you can just compare each term. This will give you, even though so each term is a different shift, but some of them are the same. Do you understand? Some of them are the same. Okay? That's the power of Vedantas. You understand? If you assume as I mentioned, so it's like a 2 free bosons. So that's why you have plane wave. But each shift is very different, but some of them are the same. Some are the same. Some is the same. So therefore, this is equal to J over 2 F and 1 and 2 or minus E3 minus whatever. IK1 minus E3 minus IK1 minus E3 IK2 minus E3 minus IK2. Okay, so this is the case. Now we find the eigenfunction, eigenvalue of Hamiltonian. So we know the system has Hilbert space of L times L minus 1 over 2. Then we just consider coherent states over this L times L minus over 2 state. But now, if you use the coordinate Vedantas, you can find the eigenvalue of Hamiltonian. Okay, so therefore E minus, this will give you E minus E0 is equal to J E minus cos K1 minus cos K2 is equal to, and if you notice, so this is equal to J1 minus cos K1 plus 1 minus cos K2. Okay. Here, so this is what we found in the one magnum, coherent state from one magnum. Okay, so it's just sum of the linear combination. It's just sum of the. Okay, so this is exactly what we expect. Sum of two one magnum, one magnum coherent state. More precise. Okay, 15 minutes left, so good. Yeah. Since this is first time to explain, so I'm very slow. 2D CFT, it's a bit, anyway. Okay, so this is what we found. Maybe we can just write down this one is equal to sum over k. No, I equal to 1 to E1 ki. E1 means the one magnum coherent states. Okay, so this is exactly what we have. And I want to keep these two equations and erase everything. Okay. Does Qian teach this x-axis spin chain? Good, there's no overlap. Okay. So this is n1, n is equal to n plus 1. And here, so if you assume this beta ansatz, coordinate beta ansatz, so coordinate beta ansatz is also valid when n1 is equal to n2. Indeed. So we want to extrapolate this equation by using this coordinate beta ansatz. Okay. So therefore, abusing this condition, which is actually abusing condition, we just assume n2 is equal to n1 plus. Okay, so abusing this condition, so the coordinate beta ansatz, we can just use this first equation when n1 is equal to n and n2 is equal to n1. Let's do some experiment by plug up into the first equation. Then you get a j over 2 for f n1, so n plus 1 minus f n minus 1 n plus 1 minus f n n. So now we have n. So n1 is going to n2 stays show up, and then minus f n plus 1 and n plus 1. Again, you have this term f n and then n plus 2. Okay. So this is what you get from downstairs, which is equal to e minus e0 f. Okay, and the subtract from here to the second equation. Okay, then we will see the condition for the two sides is equal. So if subtract equation, so the left hand side becomes maybe anyway. So if you subtract the second equation, what you get is f and n plus f n plus 1 n plus 1 minus f n equal to 0. Okay. Sorry, this is yeah, here is correct. So this term, and this term survive. Okay. The rest will cancel. Should cancel. Well, can you see that? Sorry, there are two is here. Sorry, so this term cancel with this term, and this term cancel with this term, and then 4 cancel with 2 will give you 2 here, and then these guy remain. Okay. Now, and plug, this is beta ansatz over there, that will determine the condition between A12 and A21. Okay. Condition between A12 and A21. If you plug this one into here, indeed. If you plug coordinate beta ansatz into here, this will give you to the A12, A21. Unfortunately, you have to do this kind of computation K1 plus K2 and plus A1 2 plus A21. Already exhausted. And plus 1 and minus 2 A12 e to the I K1n plus K2 n plus 1 plus A21 e to the I k1 n1 plus 1 plus k2 n. Okay, is equal to 0. Is equal to 0. The first term is really first term. Second term is really second term. And third term is this one.
So why should we make the equation to be continuous?
You mean
Why n2 equals
n1?
n1 plus 1? These two equations should be consistent.
I just assume this can be continuous by using this. This is the also include beta ansatz.
Why should we assume?
Why should we assume? I mean, we want to be. We want to have. I mean, why? I don't know why. We just want to have a continuous limit of this spin chain. So continuous limit of spin chain. Yeah, we will take the continuous limit spin chain later. So we just assume this condition can be extended to. I mean, here. So again, so here we assume these negative states have whatever essential I k1 and momentum, and a momentum, and then another. How to say spin down states? You have another e. Maybe whatever, e to the I k2 momentum, and you just consider a kind of scattering aperture. Now, by assuming this plane wave, and then the scattering is really the ratio between these two coefficients. Exactly what we have done for that function in the first lecture. And then now, so we will obtain from here we will obtain the beta ansatz equation a12, a21. Should be minus e to the I k1 plus k2. Divided by plus k2 plus 1 minus 2 e to the I. So this is beta ansatz equation you obtain. And if you assume, if you write down lambda I is equal to 1 over tangent k I over 2. If you assume this one, this is equal to, indeed, it can be written as, so this is equal to lambda 1 plus, minus lambda 2 minus 2I over lambda 1 minus lambda 2 plus 2I. If you use this variable. Okay, so this is to go, and then, so this is two body particle, the coherence states of two magnons. Coherent two magnons, so that the we can just extend it to the coherence in n magnon. So as you can easily imagine, for n magnon, you have capital N, capital N sum over beta ansatz, whatever, n1 dot n n, and sum over n1 dot n n, okay, over ni. So if you use this side, and then again you apply coordinate beta ansatz to ff, then you just have a product of this scattering amplitude. Well, at the end of the day, for n particle and coherent n magnons, what you get is indeed it's the same thing as before. e to the I k l e to the I k I l is equal to product of j is not equal to I and lambda I minus lambda j minus 2I divided by lambda I minus lambda j plus 2I. Okay. And the product is not equal to I. Okay. So that's what you obtain from the coordinate beta ansatz. And in fact, if you use the relation between lambda and ki, and this can be written as the lambda, I forgot, over lambda I plus to the L. I think plus minus I should. Anyway, so you guys understand the plus I minus I. Of course, this I is not same as this I. Okay. This imaginary number. And this is called beta ansatz equation. Equation of x. Okay. So this is the coherent state for n magnons. Coherent state at n magnon. So this is equal to. And then we can solve the lambda exactly and determine the energy of the system exactly. This can be done exactly, but I will explain this one more in detail, how to determine energy spectrum and solve it next lecture. Okay. Any question? And I will, of course, take the continuous limit as she asked, the continuous limit of this x spin stage chain. And that's called, I already forgot, what is it called? Beta, blah, blah, solution, I forgot. Beta, I'm not convinced much of it, Beta Holsen. I think he's German, okay. So from here, you get the Beta solution. Which determine energy in continuous limit. Okay, let's stop here.